Hello and welcome to another video. In this video we're going to be working on minimum cost to convert string 1. In here you have two strings, source and target, both of length n, consisting of lowercase letters, and you're given two zero-indexed arrays, original and changed, and an integer cost, where you have a cost of changing a letter to another letter. And we start with source, so you can pick a character from x, or pick a character x, change it to y at the cost of z if that's possible. Return the minimum cost to convert the string using any number of operations. If it's impossible, return -1. And yeah. And there's many indices ij where original I equals original, or original j equals original I, and changed j equals changed I. So there's not like a one-to-one mapping. So you might be able to go from like an A to an I, maybe you can go from an A to a B, and so on. Okay. And I think there's like duplicate edges as well. I don't remember if there, well, yeah, they don't really tell you that there aren't, so there could be. So there could be like an A to B cost of 5, and then an A to B cost of 7 or something like that. Okay, so basically, let's take a look. So in this first example, they say, so you already have the A, so now you need to convert the B to the C, and there is a conversion B to C here, which costs 5, so you can do that. Then you need to go from the C to the B, which there is a direct conversion from a C to a B with a cost 5, but you can also go from a C to an E with a cost 1, and then from that E to a B with a cost 2. So you're not always going to go from one letter directly to another letter. You might convert to like different letters. So if you want to go from like an A to a E, let's say, you might go from like an A to some letter, and then from that letter to the E, or some longer path. Yeah. And so the total cost is 28. And second one, so you go from all A's to all B's, so you can convert from A to C and then from C to B. So each letter is going to cost 3, so you have 12. And the last one, you can't convert from a D to an E. You can only go from A to E. So you need to convert just this D to E, and you can't. And so basically, yeah, and then the string is 10 to the 5th characters. So there's kind of a few ways to do it. The bad way would be start at every letter and then try to go from like a letter to a letter and figure out how you could do that. So maybe make a graph of like all these connections of like all these letters and all these other letters you can go to. And then every time you're at a letter, just do like a shortest path. So if you did that, you basically have like 26 nodes. And then you can have up to 26 squared edges, I guess. And then you would do this for every single, you would do like a Dijkstra's for every single letter. Maybe you can do some kind of memoization or something, I guess. So that would like limit your stuff. That probably would be fine, actually. Do this like shortest path of memoization. And then you would only get, so at the most times you could do that, so it would be like 26 by 26 combinations to go from like one letter to another letter. And then for all of those, you'd have to multiply it by like 26 times something else. So it'd be something along those lines. But the simplest way to do it is actually, first let's just get the shortest path from every letter to every other letter. And then we can easily figure out our conversion. So we'll just get like the shortest path from every letter to every other letter. And then when we're going from like an A to a B, we can just check like what's the shortest path from A to B. We have that calculated, so we can just get those. So basically, you can treat these letters as nodes, and you can treat the connections as edges. So for example, let's just like go through example 1. So if we have like an A to B, that's 1, and it costs 2. So this is 2. And then we also have a B to C with a cost 5. So we can do like B to C, cost 5. And then C to B with a cost 5. So I guess it would be like this. And then C to E with a cost 1. And then E to B with a cost 2. And then D to E with a cost 20. Do we have a D anywhere in here originally? I don't think so. Yeah, so it would be like this, I guess. D to E with a cost of 20. Something like this, right? So you can make this graph And then basically what you can do is you can do one of two things. You can do a Dijkstra's. So from every letter you do a Dijkstra's to every other letter. And then it would just be like a Dijkstra's, pretty straightforward Dijkstra's. So instead of stopping once you get to some certain node, you go to every single node and then you record those. So for A, we'll record the shortest path to every node. So we'll have like A to B will be 2, A to C will be whatever that is, and so on. And you can do that. But the easiest way to do this kind of thing is actually using Floyd-Warshall. And I was saying you shouldn't learn it because Dijkstra is more like general, but actually Floyd-Warshall is really easy. So when you want to get shortest, like if you have a graph and you want shortest path from every node to every other node, Floyd-Warshall is actually really easy to do this. So I would definitely recommend it. And I'll kind of show you in the code how to do it. And basically Floyd-Warshall is n cubed. And like I said, Dijkstra is like n cubed log n. So it's more performant and it's like way easier to code. And the idea behind it, I'll kind of show you the idea behind it and then the actual code. The idea behind it is we make, let's say we just have a small alphabet of like, let's say we have, instead of this, we only have 4 letters. So this will be like A, B, C, D. So this is our alphabet. So basically you record, like, let's say this is your x-axis and this is like your y-axis, right? So you'll have edges either be weighted or they'll either be not weighted, unidirectional or bidirectional. So for example, in our case, it's unidirectional, right? You go from source to target. So let's say this is like our source. So you can label, this is our target. And so basically we're just going to fill in like if there's something here, that means we went from this to this, because it's not bidirectional. So now you could also have this be bidirectional. So if it's bidirectional, like if you have something in this cell, let's say, that means from C to B take something and then from B to C take something. But in this case, it only means from B to C. So right away you can fill in, if it's a node to itself, these are all going to be zeros. And then everything else will be infinity. So maybe I'll put like an I for infinity or int for something. So just like these are all infinity. So this is what you initialize it to. And then for every edge that exists, then you change those values. So if there's an edge from C to B, you can just say like this is some value, maybe it's like 10. This is some value, you fill in all your edges. Let's say this is what it is. And then all you do is you just run an n cubed loop and you just see like if there's a k value I can get to from the source. So I'm basically going from source to k. And then from k to target. If that value is less than just source to target, then I will replace it. So for example, if I have like A to B right now is like 10. If I can go from like A to C to B, and that is 8, that means I will replace my A to B with 8. And this is very easy in the code, so I'll kind of show you. But basically, you're going to have this filled out. And then in the end, you're going to have all the shortest path in this adjacency list. And then all you need to check is like, okay, if I want to get C to B, I just check C to B. There will either be a value or it'll be infinity, means you couldn't get there. So it's very easy to, like, the result will be very clean. It'll be in arrays, which was better in Java. So let's take a look at the code. Okay. So we have the target length. We have the original length, and we make a graph. And like I said, using an array is going to be better. So technically, you could optimize this a little bit, but I just said, let's just make a graph of 26 by 26 because there's only 26 letters. So let's just make it 26 by 26, even though there could be less, just to keep the indexes easy. So like 0 will be A, B will be 2, or B will be 1, C will be 2, and so on. And then for every row, we just fill it out with infinity, which is max value in here. Then for every edge, we change that edge to the minimum of what that edge was, or the current edge here. And like I said, if there's duplicate edges, just keep the smallest one. So for example, if like A to B, we had 8, and now we hit a 6, we just store 6, and so on. So basically that'll fill in the initial edges in the adjacency list. Then you also, for every node, the edge to itself is obviously 0, right? Like from A to A is 0, from B to B is 0, from C to C is 0, and so on. Then here's the Floyd-Warshall, very easy. So it's just a triple for loop. where you go from the starting possible node to the last possible node. So in this case, we can have 0 to 25 is our letters. So 0, 25, 0, 25, 0, 25. And then all we have to check is, given a k value, if I to k is less than, so I guess, so this is basically the same thing. So if I to k and then k to j is less than I to j directly, we store that. So that's what it is here. So if I to k is not infinity, if k to j is not infinity, then I to j is the minimum of the old value and I to k plus k to j. And that's literally all it is. So this will give you a full out list of every node and the shortest path to every node of the nodes. It's like way simpler than Dijkstra's. Very, very easy. Basically, you just do this triple nested for loop, and then that's all you do. And now that we have everything, now we can just go through our letters, and we have the shortest paths already, so we can get all these in O of 1. So we just go through all of our letters that we need to change. We get X, we get Y, and we check, is that possible? Like if this is infinity, that means we can't change the letter, so we just return -1. If it is possible, we just update, or we just keep adding like the cost to that result. So this part's very easy. So the easiest thing to do is just first take all the letters, get all the shortest paths, and then the conversion's really easy. So I definitely recommend this because Dijkstra's is way more than this, right? Obviously, so would definitely recommend this for any graph where you need to fill out the whole graph of shortest path from every node to every other node. Now, if you just want shortest path from one node, Dijkstra's is going to be more efficient because this is n cubed. Dijkstra's for one node is like n squared, or it's typically like, depends exactly, but it's usually like n squared log n or something like that. So Dijkstra's for one node is more efficient, but for the entire graph, this is better, and this is like super, super easy. So definitely actually recommend the Floyd-Warshall. Very easy. And then we can run it, and you can see this is going to be way more efficient than using like a hash map and a priority queue and all that stuff. And if we look at these, I was talking about this in Java, pretty much all these are going to be arrays. So if we take a look at these slower ones, these are going to be like the priority queue and all that stuff. Hash map, pair, priority queue, So for more performant Java stuff, just use arrays if you can. And in this case, we can, because we can just, instead of like, I could have made a hash map here, right? This would still work. And you could still do the same thing. You could say like for every, instead of looping 0 to 26, you could say like for every value in your hash map, for every value in your hash map, from every value in your hash map, a hash map will be slower. And we can just use every letter, so it's a lot cleaner. So probably if you're coding in Java or stuff like that, I'd try to get into this habit of just using arrays when possible. So this is going to be, also time complexity is actually very easy for this as opposed to Dijkstra's. Okay, so this will basically be like, even if these are shorter, you could optimize it a little bit, but it's not going to make it that much faster. Like you don't have to use 26. You can actually like optimize a little bit, or you could like break out of these loops early if your letter isn't in here. Like maybe have like a hash set of like all the letters that actually have edges. And then if your letter isn't in one of those and like these outer loops, then just skip, because you're never going to have that. But it's not going to make it that much better. So we make a graph. So this is like 26 squared. Doesn't matter like this length. Then for every edge, we have to do this. So this is like E. And then I guess worst case scenario, you could treat it as like E. No, it's not going to be E cubed. That's for sure. It's going to be, I'd say it's probably like V cubed. Like worst case, you have V cubed. So like N cubed or V cubed or something, whatever. So I'd say this is like V cubed complexity. I'm just going to say that. And space. So we have a 2D graph. So let's call it like N squared, because worst case edges is N squared, where N is the number of letters. It's not like any of these. It's just total. So it's like 26 squared. So I guess maybe you could also say this is like 26 cubed, which actually the length of your array will be longer. So it'll be like plus, you can't have more. I guess actually you can have more edges. I think you can have duplicate edges. So it'll be like, this is like 2000. So it'll be like length of source plus like maybe like length of source plus the number of edges or something. Because like imagine you have like I don't know how many edges, but they're all duplicated. You still have to go through them all. Something like that. And then space. So the graph is 26 squared. no matter how long your stuff is, no matter how many edges. I think that's all we're storing. Yeah, so just 26 squared, so I guess you can argue constant. Yeah. Curious what it says for this. I might just copy my stuff, who knows. Let's find out. Okay, I literally just copied it. Curious if I do this, what it says. Okay, that's annoying. Okay, oh, I have to submit again, I think. Oh, interesting. Yeah, I don't know. Oh, 1. Yeah, 01 makes sense too because this is, yeah. So I guess you can say that this is constant, this is constant, I don't know. So you could write this way too, whatever. But yeah, it's going to be all for this one. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.